We're going to talk about section 7.2, areas in the plane, and we're going to try to continue to refine and develop our skill at describing what's happening on the differential level or micro level, imagining then going from a single rectangle to Riemann sum, and then getting to the integral. Some of these that we do, we will see have multiple strategies, multiple ways of conceptualizing it that will lead to sometimes different ways of solving it and evaluating the resulting area. And sometimes one will be clearly more efficient and better in that sense than the others. Other times it may be just kind of a matter of, personal preference or the way that you first see how to do it, and can you follow it all the way through to conclusion, to evaluating an integral. Many of these you may not need to do this description of the single rectangle, but I think it's a really valuable skill, and I think investing a little bit of time on these early problems that you may not really need it for will pay dividends down the road as we move into more and more complicated situations or applications, and having a well-developed skill, that well-developed kind of tool in your toolbox is going to really pay dividends down the road. So here we see an area enclosed by the parabola 2 minus x squared, we can see in yellow, and the line y equals negative x, which we can see in the green. So if we look at perhaps a representative rectangle, this is what I'm talking about in describing it on the differential level here. Now our top curve throughout the whole interval here, throughout that region, is the same. It's always going to be 2 minus x squared in this particular example. And the bottom curve, the green y equals negative x, is always the same. So this rectangle, although they may change in size as we look at them at various places, still they're going to have that same top curve, bottom curve situation. So our delta area, that area of that one rectangle, will be its base times height. The base is going to be that delta x. It's a little kind of piece of the x-axis there. The height is going to be the top curve minus the bottom curve. And so our top curve is the yellow 2 minus x squared, and minus the bottom curve, which is the negative x. And then there's our base again. So that looks like, with a little bit of cleanup, like it's going to be 2 and then a plus x and a minus x squared times delta x. So that would give us the area of one of those rectangles. We would imagine then extending that and filling this whole thing up with rectangles and adding all of those, so which would become a sum. It's going to be a Riemann sum, where we're taking that 2 plus x minus x squared times delta x, and we're adding those up with n rectangles. And you don't have to write this step out. I'm just doing it in this one case. From there, we imagine as the delta x's go to 0, that it's going to become an integral. We're going to have to figure out what those limits are, and our integrand is going to be this 2 plus x minus x squared, and the delta x will become a dx. The boundaries of our curve are going to be these points of intersection. So sometimes we'll be able to use our calculator. Sometimes we should be able to do it by hand. I'm going to do this one by hand. In future problems, we'll use our calculator and make sure we have that skill as well. So if we say the 2 minus x squared is equal to the negative x, I'm going to bring everything to the right side. So that would allow me to add that x squared. The minus x would still be there, and that would be a minus 2. We can use our factoring skills and get x minus 2 and x plus 1, which means x is going to be negative 1 or positive 2, and that's going to be the limits of our integral. Those are those points of intersection the x values that we have computed for the beginning and end of that enclosed region. You can then, this integral we could do by hand or use your calculator just for time's sake. I'm going to go ahead and just put it on my calculator and get 4.5. And so that's going to be the area enclosed by that region. Okay, let's look at another example. So I'm going to scroll up here. So now we're going to consider boundaries with changing functions. So we're going to find the area of the region bounded by y equals square root of x, which you can see in the yellow, y equals 0, which is the green, that's just the x-axis, and y equals x minus 2. You have to kind of use your imagination. The blue curve is supposed to be a straight line. It looks straighter in some parts than it does others, but that's just a representation. So we're going to look here. There's actually at least three different ways of solving this. And again, this goes back to the idea of how you perceive it or conceptualize it. And I'm going to try to use our kind of idea of describing what's happening on that differential level. So the first is maybe a standard way of doing it. I'm going to look and see that the boundaries between our region until we get to x equals 2, the top curve is going to be the yellow square root of x, and the bottom curve is going to be that green y equals 0. And so there's a representative rectangle there. But once we cross that x equals 2 vertical line threshold going to the right, then our rectangle that will show us the area of a little piece of that region is going to have a top curve still of square root of x, but now the bottom curve has changed to the blue y equals x minus 2. This will continue until we get to our point of intersection, and I think from the graph you can kind of see it looks like it's going to be at x equals 4, and we can convince ourselves if we plug 4 into the yellow square root of x, the square root of 4 is 2, so on the yellow curve that's going to be the point 4, 2, and if you do that with the blue curve, plugging in 4 for x, it will also give you 2 for y, so that is indeed that point of intersection is 4, 2. So what we are going to do now is break this into two separate integrals. So first we're going to integrate, maybe let's do our delta area. So our delta area on this first rectangle here is always going to be base times height. The base is going to be our delta x, and the top curve is square root of x. The bottom curve is 0, so top curve minus bottom curve gives us that height of square root of x, and the base is delta x. So we'll add all those up. It's going to go to an integral. As delta x goes to 0, it looks like the limits of our integral are from 0 to 2. So we will, for that first region, between x equals 0 and x equals 2, we're going to integrate the square root of x dx. Then, on the second region, we're going to get a second integral because now we have, again, our delta x, or our delta area rather, is going to be the top curve, which is again going to be square root of x, but this time minus the bottom curve is going to be minus that x minus 2, so that top curve minus bottom curve is going to be our height of that rectangle, and the delta x will still be the base, and so that looks like it's going to be square root of x minus x plus 2 times delta x for the area of that one rectangle. And again, we would sum up a bunch of them. As the delta x goes to 0, we're going to get an integral, and that's going to be the square root of x minus x plus 2, and the delta x will become a dx. We can see from our discussion earlier, the limits of our integral are going to be from x equals 2 on the left to x equals 4 on the right. And I believe if you do that, we're going to get that that's going to be 10/3. Okay, so there's the first way of conceptualizing that. is using those vertical rectangles and those two regions, splitting that up into two separate integrals. So a second way of doing this, and so this is going to be now method number 2, is to turn our attention. I don't know if I can still erase that red. I think I can. So let me rethink what we've got here now. And we will instead think of our rectangles as going horizontally. So there's going to be a representative rectangle. Now, if we're looking at the rectangles this way, then our heights, the heights of those rectangles are going to be the right curve, that blue curve, minus the left curve, which is the yellow curve for a while, and then we'll switch to be the y-axis for the other. No, I'm sorry, because our boundary was y equals 0. So we're only going to go to here anyway. So the region that we're trying to find the area of is this region, which is up in quadrant 1, since one of our boundaries was y equals 0. So in that case, the right curve, to get that height, the right curve minus the left curve will always be the same. It's always going to be the blue curve minus the yellow curve. So our delta area here, the area of that rectangle, that horizontal rectangle, is going to be, again, base times height. This time our base is going to be the right curve, that x minus 2, minus the left curve, which is that square root of x. And then it's going to be times that little thickness there, but that's now a piece of the y-axis. So that's going to make that into a delta y. So now that changes everything here, because this tells us we're going to be integrating with respect to y. So we have to come back to those functions that gave us the x minus 2 and the square root of x, and we have to rewrite those as x in terms of y. So our y equals x minus 2, we're going to now think of as x equals y plus 2. And so that's going to change that x minus 2 into a y plus 2. That's our right curve, that blue curve. And in our square root of x, where we had y equals square root of x, now solving for x, we're going to get x is equal to y squared. So our left curve, that yellow curve, the left part of our rectangle there, is now going to be a minus y squared. And there's our delta y. So now our area of that rectangle is going to be y plus 2 minus y squared, all times delta y. Now as we go to our integral, then again we have to now change our limits to be y limits. So if we look at those horizontal rectangles, defining or calculating that area between the blue curve and the white curve up in quadrant 1, then you can see we're going to go from y equals 0 to y equals 2. That was the highest we got. So our limits of our integral are 0 to 2, and we are going to get y plus 2 minus y squared dy. And if you throw that on your calculator and do f and integrate, hopefully that will also give us 10/3. So now here's a third way. This one's pretty creative, but this would still be fair game. This is still valid. So our third way is to, when we look at that, let me see if I can erase again just the red part. I don't know if it'll let me do that. Let me see. Okay, if I can do this without killing off the boundary points, I may have to redraw some of that. Put that curve back together. So now if you look at it here, a third way of imagining this is to think of this as looking at the area between our yellow curve, that square root of x, and the x-axis all the way until we get to 4. So all of see if I can shade that. So all of this region, and then after we've computed that, we can subtract off this triangle part. So we're going to think of it then, a third way of thinking of this as that integral from 0 to 4 of the square root of x dx. That's going to be all that stuff that I did cross-hatching in red, and then subtract from that the area of that triangle. That is, we can do that full integral 0 to 4 of square root of x dx, and that triangle is going to be 2 by 2, so that would be minus that 1/2 base times height. And I think if you do that, we'll still agree with the 10/3. Okay? Let's look at an even more complicated one. I'm going to slide the screen up here. So now we're going to try to find the area enclosed by y equals x cubed and x equals y squared minus 2. So the y equals x cubed, you can see that graph on the yellow, and I think we're familiar with the cube graph. X equals y squared minus 2 is a parabola. It opens to the right and has vertex at -2, 0. So we're going to try to use our graphing calculator to do parts of this. So to do that, we need to rewrite the x equals y squared minus 2 as y equals the green part, square root of x plus 2 is the top half of that sideways parabola, and the blue part, y equals negative square root of x plus 2 is the bottom half of that sideways parabola. So I have put on my calculator y1 equal to the original cubic graph, y equals x to the third, and then y2 as the positive square root of x plus 2, and y3 as the negative square root of x plus 2. So there's a couple ways we can conceptualize this as well. So one way we can do this is if we imagine now we're going to need to know what this point of whoops, I didn't want to get the eraser out. Let me redraw my curves there. And I'll switch to my red pen. So we need to know what that point of intersection is. And so here's where, again, we need to have those calculator skills. So if you, on your graph there, you can find the intersection between our y1 and y3, then I believe I'm going to call that point, whoops, this is my left hand coming in. I'm going to call that point A, and let me slide that back over a little bit. A, I believe you will find is 1.215. So that's going to be our point of intersection between the blue curve and the yellow curve. So what we can do is, if we are trying to find the area between these two curves, one thing we could do is, oops, I'm sorry, the 1.25 is actually this point right here. I think that's going to be the intersection between the green, let's see if I can erase that, the green y equals square root of x plus 2 and the yellow y equals x cubed curve. I believe this point right here, the intersection between our blue and our yellow, is just going to be -1. My graph isn't real great there, but if you plug -1 in here, you're going to get the square root of 1 is -1. So that point is -1, -1 on the blue curve, and that's the same thing you get by plugging in -1 for x into the y equals x cubed curve. So what we can do now is, if we imagine that we are going to take our rectangles vertically, so if we start our rectangle over here, then that delta area is going to be base times height, is going to be the top curve minus the bottom curve. So that's going to be our positive square root of x plus 2 minus the blue curve, which is the negative square root of x plus 2. That will be the height, and then delta x will be our base. So that is going to be 2 square root of x plus 2's, and then times that delta x. So we could do that region from -2 to -1 of 2 square root of x plus 2 dx. So that's going to give us, actually, because that point of intersection, I don't know if I can erase that. See if I can doctor this up after the fact. Yep. So I'm going to try to be sly here and make this our -1. So now I've goofed up the scale, but at least it looks a little bit better. So that's going to give us that first area of that region to the left of x equals -1. Then after we cross that point, now our rectangle is going to have a different top and bottom curve. So now our delta area for that rectangle is going to be the top curve, the green square root of x plus 2, minus the bottom curve, which is the yellow x cubed, and that will be times delta x. So we will get plus, and now our integral is going to go from the -1, where the blue intersected the yellow, all the way to our a, which we have said is this 1.215, and that's going to be our square root of x plus 2 minus x cubed dx. And I think if you do that, we're going to get, I think I got 4.215 as our area of that region. Now, a second way, so our second way of conceptualizing this is to do our rectangles horizontally. Let me see if I can get rid of the red rectangles and redraw them without destroying too much of the rest of that. Okay, so now if we imagine drawing our rectangles horizontally, then the good news is that it's always going to be, well, I guess it's going to change. So we're still going to have two integrals because of that boundary there at, no, we won't either, because we can write everything in terms of x. So let's see what our delta area is going to be. So our delta area is going to be that base times height. So it's going to be that right curve, which is x cubed. Now it looks like at first glance that it's going to change, that our left curve is going to be the blue curve part of the time, or the green curve part of the time, and a blue curve part of the time. But remember, that came from right here. And because we are going to have a delta y at the end of the day, then we are going to want to write everything in terms of y anyway. So we can use our y squared minus 2 rather than splitting it up into two separate integrals. Now we are going to have to rewrite this y equals x cubed as x equals the cube root of y. So our area is going to be that cube root of y minus y squared plus 2 after we distribute times the delta y. Now I'm going to slide this up a little bit to get a little bit more room. So we're going to get our integral, and we're going to have to figure out what our new limits are, but it's going to be that cube root of y minus y squared plus 2. The delta y is going to become a dy. So our limits of integration with respect to y are going to be at this y value up until we get to this y value there. Now the top one's not too bad, because we said earlier that was going to be, I think, at 4, 2. And so that means the upper limit's going to be 2. Now, this is going to be a little tougher. So what we need there is, I think we said the point of intersection there. Oh, wait, back up. That was not 2. So we said that the x value is going to be the 1.215. So I don't know if you still have that on your screen or you have to go back to the graph, and when you put in that 1.215, I'm going to call that y value b, and I believe that you will find that value to be 1.793 to 3 decimal places. So that's going to be our upper limit, and our lower limit is going to be this y value, which we knew that was the x value was -1, and that's going to also make the y value -1. So we are going to get that integral from -1 to that 1.793, and you don't want to use the rounded answer. You want to store that value and put it in there, and that should also give us the same result, that the area enclosed by that region is 4.215. Very good.